Hi, this is the first lesson in electronics, and in this lesson I'm going to discuss these topics. The first one is the distinct differences between electric circuits and electronic circuits. Yeah, that's very important because normally students ask what are the difference between electric circuit and electronic circuits, or sometimes students ask how to identify whether this circuit is electronic circuit or electrical circuits. Yeah, first you should know that how to identify electronic components, how to identify whether this circuit is an electric circuit or electronic circuits. We are going to discuss that first. Then second, we are going to discuss the different types of bonds in solids and lattice structure, because we know we are going to learn little bit about solids and their atomic structures and the bonds, because you know all the electronic components are made of solids. So that's the reason we are going to learn about the lattice structure and the bonds. Then third one is energy levels of individual atoms and energy bands in solids. Yes. Then fourth one, doping an intrinsic semiconductor. So after doping, it could become either N-type or P-type extrinsic semiconductor. That will be the fifth topic I am going to discuss in this first lesson. Then the sixth one is electrical properties in solids. Here only I am going to introduce certain equations like related to conductivity, resistivity, then about the mobility of electrons, mobility of holes. Those things I am going to introduce here. So until that, there won't be any equations. So here only I am going to introduce equations. Then the seventh topic or seventh title is about practice questions. So we'll do a few questions, 4 or 5 questions based on these equations. Okay, so I told the first topic in lesson 1 is we should be able to identify the distinct differences between electronic circuit and electric circuit. Okay, the first the important difference or the distinct difference is, now electronic circuits consist of active components. So electronic circuits consist of active components and electric circuits consist of passive components. So what do you mean by active components? Actually, active components, examples for active components, I can say diode, transistor, then I can say operational amplifier, short direct op-amp, then I can say integrated circuits. These are the active components. What are the passive components? Just we can say like a resistor, then I can say transformer, even capacitor, induction coil or inductor, then I can say bulb or heater. These all are passive components. So what's the difference or significant difference between active components and passive components? I have given the examples of active components and passive components. So what are the significant differences between active components and passive components? Means, you know, the passive components responds to the energy, the electrical energy flowing through them, or it responds to the voltage applied across it, or it responds to the current flowing through it. Say for example, if you apply a lower current to a bulb, the bulb will emit dimmer. It will emit light dimmer. Or if you apply lower current to a heater, the heat produced by it will be lower. If you apply larger current through it, the current becomes larger, the heat will produce larger heat, or the bulb will emit brighter light. So passive components functions or responds to the current flowing through them, but active components not like that. They do some certain operations or certain functions, but for their proper function they need additional energy. they need additional energy. For example, we are going to learn that active components are used in electronic circuits, and you know electronic circuits are used to make amplifiers. So for example, I can draw an active component or amplifier like this. So this consists of active components. So active components consists means it's used to amplify an AC signal. So the input signal you are given here may be something like this. The output signal is amplified like this. The amplitude has increased. Yes, that's the function of this amplifier. Okay, but for this active component to function, you need to supply additional electrical energy. That means without supply, this is the input electrical energy, this is the electrical input energy, and output is amplified signal. Input is low amplitude, the output is large amplitude. Yeah, but to function, for the function of the active component, it need additional electrical energy. But passive components, they don't need any additional electrical energy. But for active components, they need additional electric energy or circuit that we need to make to give additional electrical energy for the function of the active components. So that's the difference between active components and passive components. But diode, you might ask, can it function as a passive component? Yes. Only the diode can function as a passive component also, but sometimes it used in electric circuits also, but only the diode could be either, we can think about it as a passive component or active component, but it's made of semiconductor, I'll tell you, right? So, but transistor, operation amplifier, electric integrated circuits, they all are perfectly active components. They can't behave as a passive components because for their function, they need additional power supply or additional circuit should be completed for their proper function. Okay, so this is the first difference between electric circuit and electronic circuit. Okay, so these are the active components, these are the passive components. So the second difference I can say, the active components are made of semiconductor. They all are made of semiconductors. But passive components are made of, normally they are made of conductors or metals. So that's the second difference I can say. The active components, all of them are made of semiconductors. You can't make diode, transistor, operational amplifier or integrated circuit by using metals or conductors. They must be made of semiconductors. But passive components are made of mostly conductors. Even a capacitor is made of metal. Actually, you know, their capacitor consists of two parallel plates. We learned that in A level. So consists of two parallel plates. They are made of metals. In between, you can give some dielectric metal. Even you can leave it as air, right? So actually, the capacitor is also made of conductor. Induction coil or inductor is made of copper wire. So you can just wound a copper wire in the form of solenoid. Yeah, that's the inductor. Even resistor, you know, it's made of nichrome wire mostly. Transformer consists of primary coil, secondary coil, iron core. They all are made of metals, right? So they all are made of conductors, but all the active components are made of semiconductors. That's the second difference. Okay, the third difference we can say like this. Right, so the third difference, the electronic components are the circuits. The electronic circuits are used for special type of functions like digital processing, signaling or signal processing, switching, amplification, modulation, demodulation. So these type of specific functions are done by electronic circuits. But electric circuits, they do just transferring energy through their circuits, their components. Say for example, here just capacitor is used to store energy, inductor is used to store energy in magnetic field, or it's used to create magnetic field around it. Same way resistor is used to control the current flow or change the potential in other components. Transformer is used to increase or decrease the amplitude of an AC voltage. Same way, like a step-up transformer, step-down transformer. Bulb is used to give just electrical energy. Heat is used to give just heat energy. But these are the normal function of electrical circuits, but electronic circuits have completely different type of functions. I already told that they are used in digital processing, amplification, switching, modulation, demodulation, then filtering. All these special type of functions are done. They actually, these electronic circuits, they do this type of special type of functions, right? So these are the three main differences between electric circuit and electronic circuit. Okay, so I told that as a second difference, all these active components are made of semiconductors. So in this topic we are learning about electronics. So since electronics is a part of physics, part of science, and these components are made of semiconductors, we should know the special property or the favorable property of semiconductors compared to conductors and insulators to design or make electronic components. So that's the next topic we are going to learn in this lesson one. Mainly that's a remaining part of this lesson. We are going to learn about semiconductors and their favorable properties or distinct properties compared to solid conductors and insulators. So to learn that, we need to know about their lattice structure, about semiconductor, the bonds formed by semiconductors, then how to dope. All those things we are going to learn in the following topics. Okay, so now we are going to learn different types of bonds in solids and lattice. Okay, you know that in atoms the last orbit is called valence orbit or valence shell, and the electrons in that shell is called valence electrons. So these are the electrons involved in forming chemical bonds. You know that, not necessary for us, but anyway, atoms they form bonds to get stable electronic configuration in their last orbit, is it? So in solids we know that atoms are tightly bound together. So there are huge number of atoms are packed together very closely, and you know that structure extends in all three dimensions. That is called lattice structure. So in solids we call about lattice, the word lattice structure only for solids, not for liquids, not for gases. So there the lattice means repeated arrangement of atoms due to their bonds with the neighboring atoms, which forms a three-dimensional structure or crystalline structure, that is called lattice. There are different types of lattice, body-centered cuboid, face-centered cubic, hexagon. We don't need them. But anyway, depending on the type of or the structure of the lattice, the properties of the solid varies. For example, properties means electrical conduction, then thermal conduction, then physical strength. These all depends on the type of lattice they form. Right, anyway. That we don't need much in this topic. We are learning about electronics here. Okay, so I told that the last orbit electrons form the bonds with the neighboring atoms to get stable electronic configuration. There are three different types of bonds. In solids, the atoms, they form three different types of bonds with the neighboring atoms. The first one is called metallic bond. You learn that in chemistry. I am not going to do in detail. The second one is called ionic bond. And third one is called covalent bonds. Okay, so the metallic bond is only between two or different types of metals. Say for example, in metals, when you consider two metal atoms, the distance between their neighboring nuclei the distance between their neighboring nuclei is smaller than the diameter of the atom. So that means the last orbit electrons, the valence electrons, will overlap heavily between each other among them. So due to the heavy overlapping of valence electrons, what happened? They form a special type of bond called metallic bond. That's enough for us in this lesson. Then ionic bond means ionic bond occurs between a metal atom belongs to a metal and an atom which belongs to a non-metal. So when a metallic atom and non-metallic atom uh, uh, creates a bond among them, what happens? The metallic atom will lose electron and it will become positive ion. The non-metallic atom will gain the electron lost by the metallic atom, and the non-metallic atom will become negative ion. So there are positive ion metallic atom and the negative ion non-metallic atom. Among them there will be electrostatic attractive force. That electrostatic attractive force forms the ionic bond. So the difference between metallic bonds and ionic bond, metallic bonds, what happens? The last orbit electrons are overlapping heavily among them because the distance between the nuclei is smaller than the diameter of an atom, so they overlap heavily. Because of that overlapping, they form a bond called metallic bond. Here, metallic atom and non-metallic atom, they form ionic bond. The metallic atom loses an electron or two electron, depends. The non-metallic atom gain the electron lost by the metallic atom. So the metallic atom will become positive ion, non-metallic atom will become negative ion. So between positive and negative ions there will be electrostatic attractive force that forms the ionic bond. Okay, covalent bond. We are interested about covalent bond because you know the silicon, germanium, those are the elements used in making of semiconductor device components. So covalent bond means they are neither atom lose or gain any electron. They share the electrons. So they don't lose or gain, they share the electrons among them. Due to sharing the electrons among them, the bond formed is called covalent bond. So remember that the material those are used in design or making of semiconductor components such as diodes, transistors, integrated circuits, operational amplifiers, they all are semiconductors. All semiconductors form covalent bond, and that bond is very useful. The property of these covalent bonds are very useful in designing these components because we are able to dope. I'm going to tell about these things. Doping means adding some other elements to the semiconductor and we can create different electrical properties. So that's the very helpful for or favorable property of this covalent bond. Okay, we are going to learn about we are going to learn about energy levels, and later we'll discuss about doping, right? So covalent bond is the most favorable bond in electronics. Okay, so the next topic is energy levels of individual atoms and energy bands. Okay, we learned that in A level that according to Bohr model, an atom consists of different discrete energy levels or different discrete shells, and electrons are consist on those shells or energy levels, right? You know that Bohr model. So we can draw the Bohr model, either nucleus at the center and different shells like this, discrete shells, and each shell has a specific energy. The closest shell is called ground state, first excited state, second excited state, and so on. Or we can draw these shells in the form of energy levels like this, and this is called the ground state, first excited state, second excited, and so on. So this is according to Bohr model, and this representation is only for individual atoms. But when we consider solid, you know, we learned that even in year 10 or 11, the solid consists of huge number or large number of atoms, they are very closely packed together. We learned that the differences between solids, liquids and gases. We say solids, atoms can't move freely. Atoms only can vibrate about their fixed position. In liquids, the molecules can slip over each other. In gases, we can imagine the gas particles we normally say, or the atoms in gas, are free to move. So in solids, we know that atoms are very closely packed together and there are larger number of atoms. So what happened? In solids, we can't ignore or we can't neglect the influence of neighboring atoms on the other atoms. So that means in liquids, the atoms are far apart. So the energy levels of the individual atoms won't have any interference among them much. In gases, we can neglect it. But in solid, what happens? If you think about a specific atom, on that atom, all the neighboring atoms will have influence in terms of electrostatic force. So what happens in solids? These energy levels are closely packed together and overlap with each other. So due to the overlapping property, due to the overlapping of energy levels of the neighboring atoms, what happened? We don't consider, when we think about electrical conduction, we don't consider the individual energy levels of atoms in solids. But in chemical reaction, when you think about chemical reaction, yes, we need to consider the individual valence electrons that forms the chemical bonds. But when we think about electrical conduction, you know that the electrons in the last orbit, or the conduction electrons, it jumps from one point of the solid lattice to another point of the solid lattice. So lot of individual atoms involved. So we don't consider the properties of individual atom. We consider collectively different situation or different thing that is called energy bands. So they are what we consider when we think about electrical conduction in solids, not in liquids, not in gases, only in solids. Due to the overlapping of energy levels, they merge together and we define two different types of energy bands. They are called valence band and conduction band. So what is valence band? All solids, all three types of solids, conductors, semiconductors, insulators, all three types of solids have two different bands called valence band and conduction band. You know the reason why do we consider bands rather than individual atoms. The reason, in solids, the atoms are very closely packed together, energy levels overlap with each other, and when we think about electrical conduction, not only one atom, the whole lattice involves in electrical conduction. Therefore, we need to think about the outcome of merging, overlapping energy levels that forms the energy bands. So there are two different types of energy bands, valence band and conduction band. So their valence band means, valence band, you know that normally the reason why these solids, they form chemical bonds with the neighboring atoms to get stable electron configuration. So I told that in in semiconductors, they form covalent bond to get the required electronic or electric the electron configuration. So there actually we can imagine the valence band is the valence electrons that provide the required electron configuration. So valence band means it consists of electrons in the valence orbit of individual atom and all the electrons in the inner orbits of the atom. So the valence band means it consists of valence band consists of all the electrons in the valence orbit of the atom and the electrons in the inner orbit of the atom. And valence band, we can say at 0 degrees Celsius, the valence band is completely filled band, because you know the solids, this valence band is only for solids. In solids, they create bonds to get the stable electronic structure. So there they have obtained the required electronic structure, filling structure they get it. Therefore we say the valence band consists of all the filled electronic or all the filled orbits of an atom. That's a valence band. Then the other one is called conduction band. Normally conduction band is above the valence band. This is called conduction band. Conduction band. Always the conduction band at 0 degrees Celsius won't have any electrons, but conduction band means it consists all the conduction electrons. The electrons those can participate in electrical conduction. Okay, so I just drew it. Now I'm going to draw again the same diagram for conductors, semiconductors and insulators separately. So when I think about these two type of bands for conductors, what happens? I told that in conductors the valence orbit of individual atoms, they overlap with each other. So because of that, in conductors the valence band, this is valence band, this is in conductors, and the conduction band will partially overlap or almost closely overlap. This is conduction band, so I blue color. So in metals, the valence band and conduction band, they partially overlap or almost they overlap with each other. But when you consider semiconductors, there will be a distinct gap between the valence band and conduction band. This is semiconductors, and this is the conduction band. So there will be a specific or well-defined energy gap between them. That's called energy gap or forbidden gap. Or energy gap. That is the semiconductor. We are interested about this type of energy bands, not this one, because semiconductors have this specific type of energy bands. I'll explain that. Then the insulators, they also have separate insulators. They also have separate energy bands, but the gap between the valence band and conduction band is very large. So compared to semiconductor, in insulators, the gap between the valence band and conduction band is very large. So valence band consists of all the valence electrons of the atoms and inner electrons also. Right, now we'll analyze separately. So conductor, what happened? The valence electrons and the conduction electrons are overlapping with each other. You can't separate them. So that's the reason conductors conduct electricity very well, because they have plenty of conduction electrons, because valence electrons also partly involved in conduction. But when you think of semiconductors, there's a gap between valence band and conduction band. I can shade them. This valence band I can shade with green color. So there's a gap between valence band and conduction band. So this gap for a particular semiconductor, this gap remains constant. What happens at 0 degree Kelvin or 0 Kelvin, absolute 0, all the electrons will be in the valence band and conduction band will be empty for semiconductor. At 0 Kelvin, absolute 0, the conduction band is empty. So that means the semiconductor will not involve in electrical conduction, because electrons in the conduction band, they involved in the electrical conduction, not the electrons in the valence band. Like I already told, the electrons in the valence band, they are bound to the individual atoms, so they can't move freely. But what happens when the temperature increases? We say normally at room temperature, what happens? The electrons in the valence band can absorb the thermal energy and they will be excited from valence band to conduction band. So like that, when the temperature increases, more and more electrons will be excited from the valence band to the conduction band. So when the electrons are released from the valence band, there will be vacancy, electron vacancy in the valence band. That electron vacancy in the valence band is called hole, H-O-L-E, hole. That's called hole. Okay, we'll go to the insulators. In insulators, also same two different discrete bands in the here the conduction valence band. Here the valence band, and here is the conduction band. But the problem here, the gap between the valence band and conduction band is very large, and the electrons cannot be excited even at higher temperature from valence band to conduction band. So insulators never become, they won't be able to conduct electricity even at higher temperature, because the electrons cannot be excited by absorbing thermal energy. They cannot be excited from valence band to conduction band, because before they are excited due to high temperature, the insulator might be burned. So that's the reason insulators won't involve in electrical conduction. In semiconductor, again, electrons can be excited from valence band to conduction band. At 0 Kelvin, absolute 0, yes, conduction band is empty. So the insulator behaves like, semiconductor behaves like insulator at 0 Kelvin. But when the temperature increases, semiconductor, what happens? The electrons absorb the thermal energy and they will be excited from the valence band to conduction band. So the electrons are excited, there will be a void, or there will be a gap in the valence band, and this will be excited to the conduction band. So there will be free electrons or delocalized electrons in the conduction band. So when one electron is excited from valence band to conduction band, there will be one hole, hole in the valence band, and there will be one delocalized electron in the conduction band. When two electrons are excited from valence band to conduction band, there will be two holes and there will be two conduction electrons in the conduction band. Now this vacancy, after electron is excited, there will be vacancy in the valence band. This vacancy has the ability of attracting neighboring electrons from the valence band. So the hole behaves like a positive charge, because the hole functions or behaves like a positive charge because it has the capability of attracting electron towards it. Because if there's a vacancy, other electrons in the valence band can jump to this hole. So hole, when it accepts electron, means it behaves like a positively charged particle. So we normally say the charge of the hole is plus 1.6 10 to the power minus 19 coulomb. That is same as the charge of an electron. Okay, so the hole can attract electrons from the neighboring atoms of the valence band. So hole behaves like a positively charged particle, and its charge also taken as same as electron, but it is positive side. Okay, so I told that valence band consists of valence electrons of individual atoms and the electrons from the inner orbits. So electrons in the valence band are not free to move. Normally they don't move. Electrons in the conduction band involved in the electrical conduction. So in conductors, valence band and conduction band overlap partially or almost completely they overlap. So there is no energy gap between valence band and conduction band in conductors. Therefore, even the valence band involves in electrical conduction in conductors or metals. But when you think about the semiconductor, there's a gap between valence band and conduction band. At absolute zero, the conduction band is empty. So semiconductor cannot involve in electrical conduction at absolute zero. It behaves like an insulator. But when at room temperature, electrons can be excited from valence band to conduction band. When the electrons are excited from the valence band to conduction band, they leave a void or hole in the conduction band, and that hole has a behavior or nature of attracting neighboring electrons in the valence band. So the electrons have other electrons in the valence band has tendency of moving towards the hole. Therefore, hole has charge which is equal to plus 1.6 10 to the power minus 19 coulomb, because it has the tendency of attracting neighboring electrons in the valence band. Insulators, they also have valence band and conduction band, but the band gap or the forbidden gap is very large, and electrons cannot be excited from valence band to conduction band even when the temperature is increased. So what happens, before the electrons are excited, the material will burn. All these band theories are only for solids, not for liquids, not for gases. Okay, so motion of charged particle is called current flow. Rate of flow of charge is defined as current flow. So we'll think of like this way. Now, when we, I already told that in semiconductors, electrons in the conduction band, they involve in current flow. So we'll leave that just now. We'll think about the holes. What happens when holes move? Will there be a current flow? Yes, we say the current flow due to movement of hole is called hole current. Say for example, what happens now? Imagine imagine just an analogy. Imagine there are few some plates are kept like this. Just an analogy I'm using before explaining how hole current is created. For that I'm using an analogy. So imagine there's a vacancy, but here there are some balls kept like this. Few balls are kept on these plates. Right, imagine when this ball moves to the left, if this ball moves from here to here, if I draw the diagram again, you can see now the first plate or first sheet has gained the ball, the second has become empty, third is there, it consists, now fourth is there, consists, and the fifth one also has the metal. Right, now when this ball moves to this empty sheet, what happens? This will remain there. This will gain this ball, but this one will become empty. This will be there, and this also will be there. Now think about this ball moves to this plate. What happens? Same thing again. This will be there will be the ball. This is gaining a ball, right? And here this become empty, here there will be a ball on the last. Again the last example, if this moves to this side, what happens? Again I can draw the same diagrams like this way. This has become empty. Now look at here, if you compare from the first to the last diagram, this is the first diagram, this is the second diagram, third diagram, fourth diagram, fifth diagram. So this happened during a particular time period. Yeah, this is initially when t equals 0, and later this is at time t equals t1. So throughout this time, this movement of balls occurred on different plates or whatever it is, on different sheets or whatever it is. So you can see initially the empty or the vacancy was on the first sheet, and at time equals 0, the vacancy was at the first sheet, and at time t equals t1, the vacancy has gone to the last sheet. So actually what's happening, the balls are moving towards left. They are moving towards left. So when the balls are moving towards left, the vacancy is moving towards right. Understand? So vacancy is moving towards right. Okay, so this analogy, I can use it to explain the current flow in semiconductors, how the current is created by holes in semiconductors. See, for example, imagine a semiconductor strip. So there I am considering only the valence band. I am not considering the conduction band. Electrons in the conduction band, they involved in current flow. We know that. You know that you learned in electricity in A level or O level. When you connect a power supply to a material, inside the material, electric field is created. Due to the electric field, electrons will be dragged, and that's the reason for the current flow. So imagine this is the valence band. So this is the conduction band. This is the conduction band. So this is the material. So in this material, this is the material. In this material, these two bands are there, right? So when you apply external electric field by connecting it to a power supply, something like this. When you connect it to a power supply, this is the positive terminal. When you connect it to a positive terminal, negative terminal of a power supply to this semiconductor material consists of two different bands, valence band and conduction band. Electrons in the conduction band will move. Which direction will they move? You know, the electric field will be created inside the semiconductor. This is positive terminal, this is negative terminal, means the direction of the electric field inside the material will be towards right. This is the direction of the electric field from positive to negative. So the electrons in the conduction band, they will move opposite the direction of field lines. We learned that in A level under electric field, always negative particles move opposite the direction of field lines. So the electrons will move towards left. In the conduction band, electrons will move towards left. That means current flow in the conduction band will be towards right. Due to the flow of conduction electron, the current flow will be towards right. Now think about valence band. So the electrons in the conduction band are excited from valence band. You know that I told normally at 0 Kelvin there won't be any electrons in the conduction band. Whatever the electrons in the conduction band are excited from the valence band. So if there are 1 million conduction electron, there will be 1 million holes in the valence band, because all the electrons in the conduction band are excited from the valence band. I already told that, right? So in valence band, what happens? There are 1 million, or if I say there are 1 million conduction electron, there will be 1 million holes in the valence band. Okay, now we'll think about a hole. What happens? So I told that same way. Now I told that the hole behaves like a positive charge. So here inside this is the positive charge. This is the positive plate. So this is the battery which is connected to this side, means this is the positive end, this is the negative end. So the electrons are moving towards left, means the holes behave like, I told they behave like positive charges. So the hole will move towards right in the valence band. The hole will move towards right in the valence band. So there will be current flow due to hole in the valence band towards right. Hole current we call IH. So the current flow in the semiconductor, this is a semiconductor. This semiconductor has two bands, valence band and conduction band. So in conduction band there is current flow due to delocalized electrons, that is towards right. Because electrons are moving towards left due to this power supply, electric field is created towards right. So the electrons will move towards left, and the current flow due to the flow of electrons is towards right. In the valence band, there will be current flow. That is due to flow of holes. I told holes behave like positive charge because holes have the intention of attracting neighboring electrons in the valence band. So the hole will behave as a positive charge. So that will move in the direction of electric field. So there will be current flow in the hole, in the valence band due to holes, that will be towards right. Now you can see the direction of current due to conduction electron and the direction of hole due to, direction of current due to hole, direction of current due to conduction electron and the direction of current due to hole, both are towards right. That means both are in the same direction. Therefore, I can say the current flow in the semiconductor is equal to current due to conduction electron plus current due to holes. Important conclusion. Okay, so this is the lattice structure of intrinsic semiconductor. Intrinsic semiconductor means a pure semiconductor without any impurities. Now in physics or electronics, we don't consider transition metals. So we say in periodic table, semiconductors belong to group 4. But in chemistry students, they say they include the transition metals and they say semiconductors belong to group 14. Anyway, whatever it is. So we consider normally group 4 elements semiconductors because we don't consider transition metals. We don't need that in physics or electronics. But chemistry students, they include transition metals and they say periodic table consists of 18 groups and this semiconductors belongs to 14 group, whatever it is, right? Okay, so you know these semiconductors consist of 4 valence electrons and this is the covalent bond. I told that during the start of this lesson. So covalent bonds are formed with the neighboring atoms. Actually, this is the 2-dimensional representation of 3-dimensional lattice. You know what's the meaning of lattice, I already explained. So this is the 2-dimensional representation or 2-dimensional diagram of a 3-dimensional lattice. So you can see this silicon atom. These 4 electrons are its valence electrons. It shares these 4 electrons with 4 neighboring silicon atoms and it's getting total electron configuration of 1, 2, 3, 4, 5, 6, 7, 8. So 8, that is a stable electron configuration. So the silicon atom is in a stable state in terms of electron configuration. So this is called intrinsic semiconductor. Now we can dope this intrinsic semiconductor with either group 3 elements. If I don't consider transition metals, I'll say with group 3 elements and or with group 5 elements. If I include the in the periodic table as chemistry students, if I include the transition metals, I can dope these semiconductors with group 13 elements or group 15 elements. Either way we can say. So doping means adding impurities from either group 3 or group 5 to the lattice of intrinsic semiconductor is called doping. Then after doping, the intrinsic semiconductor which accepted or replaced certain silicon atoms will be replaced by these elements from group 3 or group 5. So that is called extrinsic semiconductor. So that's the next topic we are going to do about extrinsic semiconductor, how it works, what's the advantages of having doping. Okay, so what is doping an intrinsic semiconductor? Intrinsic semiconductor means I already told it's a pure semiconductor. So what is doping means intentionally introducing an impurity either from group 3 or group 5 into the intrinsic semiconductor to change its electrical conduction or electrical property is called doping. So that is called doping. There are different methods of doping. Okay, so intentionally introducing either group 3 elements such as aluminium or boron or indium or gallium to the intrinsic semiconductor, or introducing group 5 elements such as group 5 element such as phosphorus, arsenic, antimony to the this intrinsic semiconductor is called doping. So these impurities, those are introduced into the semiconductor, either group 3 element or group 5 element. Those are introduced, either one of it introduced into the semiconductor is called dopant. That is called dopant. So element which is introduced to the pure semiconductor is called dopant. It could be either group 3 element when we don't consider transition metals. In physics, we don't consider transition metals. If you think about transition metals, the periodic table with transition metal, that will be group 13. So I'll put both group 3 element or group 13 element. Either one we can use, or the other type is called group 5 or group 15 if we consider the transition metals, group 13 and group 15. But physics, we don't consider transition metals, so we do say periodic table, this is group 3, this is group 5, and the pure semiconductors are group 4. So group 3 elements, you know what are the elements in the group 3, we don't need much, but in chemistry students, you know that group 3 elements are either boron or aluminium, gallium, indium. So we don't these things, indium. So group 5 elements are, we normally use phosphorus, or we can use antimony, or we can use arsenic. Normally they use phosphorus as the group 5 element. So these are called dopant. Those are introduced into the pure semiconductor. Okay, so doping can be done in different methods. The common methods are diffusion method, and the second one is called ion implantation. Either way, the intrinsic semiconductor could be doped with either group 3 or group 5 elements. So diffusion method means in both methods anyways, the intrinsic semiconductor will be kept in the form of like a wafers, right? Like a layers, right? So there, in the diffusion method, what happens? The dopant will be heated in the form of gaseous state, and it will be passed through the semiconductor which is at high temperature in the form of wafers, and the semiconductor will absorb the dopant, and the dopant, after they are absorbed, they will stay inside the semiconductor. That is first method. In the second method, ion implantation, what happens? The dopant, that is group 3 or group 5 elements, they will be in the form of ions, and they will be accelerated by using strong electric field, and they will bombard the semiconductor which is in the form of wafers. So when they bombard, they will penetrate into the semiconductor, and they will be inside the, or they will become incorporated into the semiconductor, right? So that's a method called ion implantation. So after doping, annealing process happens. What they do, they heat the doped semiconductor to higher temperature to rearrange the impurities in the lattice structure to form a proper lattice structure. And also this heating annealing process will help to repair any damages caused to the semiconductor during doping process. Okay, after doping, the semiconductor is called, after doping the semiconductor is called extrinsic semiconductor. So here we know that group 3 elements are actually used to dope the semiconductor into a specific type called p-type semiconductor, and the group 5 elements are used to dope the semiconductor to n-type semiconductor. We are going to discuss those next. Before that, I will draw the lattice structural diagram for both p-type and n-type extrinsic semiconductor after doping an intrinsic semiconductor. Okay, so when you dope a silicon with group 5 elements such as proton, what happens? You know, proton group 5 elements have 5 valence electrons. Last orbit, they have 5 valence electrons. So out of those 5 valence electrons, I drew with red color the 4 valence electrons of the phosphorus will form covalent bond with the neighboring silicon atoms. Here this also two-dimensional representation of three-dimensional lattice structure. So I can say that the phosphorus has five valence electrons. Out of those 5 valence electrons, 4 valence electrons form covalent bond with the neighboring silicon atoms, and there is a extra valence electron provided by the phosphorus. So this extra valence electron could be easily excited from the valence band to conduction band even at room temperature. So this extra valence electron of the phosphorus will become part of the conduction electron. So you can see that this diagram, out of all these silicon, only one silicon which I drew earlier, intrinsic semiconductor, I drew it earlier, the lattice structure, only one silicon atom is replaced by a phosphorus. So that one phosphorus atom will provide an extra valence electron to the conduction band of this extrinsic means which is pure semiconductor with impurity. Here the impurity is phosphorus. So this extra electron will be excited to the conduction band of the this extrinsic semiconductor lattice. So that will involve in electrical conduction. So that means here you can see that when this electron is excited to the conduction band, no hole is created. Careful. I told that when you think about pure semiconductor, intrinsic semiconductor, there will be valence band and conduction band. I drew it already. This is the band gap or forbidden gap. So I told this is the valence band. I shortly write V dot B dot. Conduction band C dot B dot, shortly I write. So I told that when I was explaining about the electrical conduction in intrinsic semiconductor, which is pure semiconductor, I told that when an electron is excited at room temperature, when an electron is excited from, in semiconductor, electron is excited from valence band to conduction band, it will leave a hole here and the conduction band will get the free electron. So I told that there will be equal number of holes and conduction electrons in intrinsic semiconductor. If there is 1 million holes in valence band, there will be 1 million conduction electrons in the conduction band in intrinsic, that is pure semiconductor. But here what happens when you are doping with phosphorus, that is group 5 element, what happened? It is giving an extra electron, and that extra electron will be excited to the conduction band without any creation of holes. So without creation of holes, we will get extra conduction electron. So when we dope with, for example, 10 million phosphorus atoms, we will get 10 million additional conduction electron without creation of holes. So intrinsic semiconductor initially had same number of holes and electrons. Now this number of electrons will be increased by 10 million because I told, for example, 10 million phosphorus atoms are doped with intrinsic semiconductor to form extrinsic semiconductor. So the number of conduction electrons in the conduction band will increase by 10 million. So in n-type semiconductors, carefully listen, in n-type semiconductors, the number of electrons, the conduction electrons will be much larger than number of holes in the valence band. So there we can say in n-type semiconductors, the electrical conduction is mainly due to conduction electrons, and the current due to the holes is negligible. Very important conclusion. Again, the current flow in the n-type semiconductor or n-type extrinsic semiconductor is only due to electron. The current flow due to holes is negligible because number of holes in the extrinsic n-type semiconductor is negligible compared to number of conduction electrons in the conduction band. So the group 5 element such as phosphorus, which provide an extra electron, is called donor. That group 5 element is called donor atom or donor element. Okay, now we'll think about p-type semiconductor. So to get p-type semiconductor, we should dope the intrinsic semiconductor such as silicon with group 3 elements such as boron. When you dope it with boron or aluminium, what happens? The boron or aluminum, they have 3 valence electrons and 3 valence electrons. So these 3 valence electrons are forming bonds with the 3 neighboring silicon atom, and there is a void. There is a shortage of electrons because boron has only 3 valence electrons. So it will provide a hole in the valence band. So there is a shortage of electron which is forming a bond with the silicon. So what happens? There will be a hole or void in the p-type semiconductor. So this hole will stay in the valence band of the p-type extrinsic semiconductor. So when you think about this p-type extrinsic semiconductor, same way I can draw the diagram here. This is the valence band. This is the conduction band. So earlier I told what are the number of intrinsic semiconductor, pure semiconductor, the number of holes in the valence band will be same as number of conduction electrons in the conduction band. Now these holes will stay in the valence band without any excitation of electrons to the conduction band. So for example, if we dope intrinsic semiconductor silicon with 10 million boron atoms, there will be 10 million additional holes in the valence band without exciting electron to the conduction band. So here the number of holes per unit volume will be much larger than number of electrons in the conduction band. So in p-type semiconductors, the current flow is only due to or mainly due to holes. So current flow due to the conduction band is negligible. So in p-type semiconductors, we can say the current flow in the p-type extrinsic semiconductor is due to holes, and the current due to conduction electrons is negligible. So here we say in p-type semiconductors, holes are the majority carriers because they are the main charge carriers involved in electrical conduction. Same way in n-type semiconductors, majority carriers are electrons. So here minority carriers, those are not much involved in electrical conduction, or the electrical conduction is negligible by the electrons. So in p-type semiconductors, electrons are the minority carriers, and n-type conductors, minority carriers are the holes. Again I am telling, in n-type semiconductors, minority carriers are holes and majority carriers are electrons. In p-type semiconductors, majority carriers are holes and minority carriers are electrons. So here the group 3 elements are called acceptors. They are called acceptors. Group 5 elements are called donors. Okay, so to dope a semiconductor to n-type, the semiconductor should be doped with group 5 element such as phosphorus. The phosphorus has 5 valence electron, and 4 valence electron will involve in covalent bond with the neighboring silicon atoms. So the extra valence electron of the phosphorus will be excited to conduction band of the extrinsic semiconductor. Extrinsic semiconductor, which consists of phosphorus, also will be excited to conduction band without creation of any holes in the valence band. So there will be larger number of conduction electrons in the conduction band. So the conduction electrons will become majority carriers in N-type semiconductors. Same way, when a semiconductor is doped with doped to a P-type semiconductor, so the semiconductor such as silicon or germanium should be doped with group 3 elements such as boron or aluminium. There will be extra hole provided by the dopant. So the extra hole will remain in the valence band of the extrinsic semiconductor after doping. So there will be hole in the valence band without exciting any electron to conduction band. Therefore, after doping the semiconductor with group 3 element, there will be larger number of holes in the valence band, and number of conduction electrons in the conduction band will be much smaller compared to number of holes in the valence band. So when external voltage is applied across this p-type semiconductor, there will be current flow due to movement of holes. There will be current flow due to movement of conduction electron also, but that will be negligible. So majority carriers of the p-type semiconductors will be holes and the minority carriers will be electrons. Okay, so after doping, what happens? The material, the doped material will be used to create electronic components such as transistors, diodes, operational amplifiers or integrated circuits. That is called fabrication. That process is called fabrication. Okay, so now we came across the diagram. So how many dopant should be needed to dope a semiconductor? So if you want to dope an intrinsic semiconductor, how many dopants should be needed, or how many atoms from the group 3 or group 5 should be added to intrinsic semiconductor to create an extrinsic semiconductor? Okay, so to understand that, we'll do a calculation, a question based on calculation next. Okay, so in this question, it's mentioned that at room temperature, charge carrier density of intrinsic silicon is 10 to the power 16 per meter cube. That means in intrinsic semiconductor, the delocalized electrons or the conduction electrons per meter cube is 10 to the power 16. Now they are going to dope it with phosphorus, means it's a group 5 element, in order to convert this intrinsic semiconductor to an N-type semiconductor. Now after doping, they are expecting to have an increase this charge carrier density by a factor of 1 million. Okay, so I already explained that when you are doping an intrinsic semiconductor with either group 3 element or group 5 element, the dopant will provide only one free electron to the conduction band if it is doped with group 5 element, or it will provide only one hole per atom or per impurity atom if it is doped with group 3 elements. Say for example, if you dope a semiconductor with 1 million phosphorus atoms, each phosphorus atom will provide a free electron to the conduction band of the extrinsic semiconductor. So there will be increase in 1 million conduction electrons. So here they want to increase it by a factor of 10 to the power 6, means now they are expecting new delocalized electrons or number of electrons in the conduction band, that is charge carrier density. The new charge carrier density, they are expecting it to be 10 to the power 16 into 10 to the power 6, that means 10 to the power 22 per meter cube. That is the expected charge carrier density. Okay, so first we will find how many dopants or how many impurity atoms, phosphorus impurity atoms should be added per meter cube to get this number of delocalized electrons or conduction electrons in the extrinsic semiconductor after doping. We'll find it per meter cube, right? How many phosphorus atoms should be added per meter cube to have this number of conduction electrons per meter cube. Then we will find in an intrinsic semiconductor how many, so here they are given the density of the silicon, molar mass of the silicon, Avogadro number. So by using those, we will find how many silicon atoms exist in an intrinsic semiconductor per meter cube. We will find it. Then by using in 1 meter cube this much of intrinsic semiconductor, there will be silicon atoms. We know that. We know how many phosphorus atoms should be added per meter cube. Then we can find how many, what's the ratio, say for this number of silicon there should be this number of phosphorus per meter cube. So that will give the final answer. So I'm going to do that way now. Okay, so here we know that in intrinsic semiconductor, the charge carrier density, the number of electrons in the conduction band per meter cube is 10 to the power 16. So we can say Ne, that is 10 to the power 16 per meter cube. Okay, so after adding certain number of phosphorus atoms per meter cube, we will get an extrinsic semiconductor in which the charge carrier density in the conduction band should be this into 10 to the power 6, because we had increased it by 10 to the power 6 times. So we can see the number of phosphorus atoms added per meter cube, let it be N naught per meter cube. So that's the number of phosphorus atom added per meter cube. So after adding, each phosphorus atom will give one conduction electrons to the conduction band. So after adding it, then the extrinsic semiconductor should have the total delocalized electrons per meter cube is 10 to the power 22. So I can say initially I took it Ne. So after that it should be 10 to the power 6 Ne. Anyway, I know the value 10 to the power 6 into 10 to the power 16 for the extrinsic semiconductor. That is equal to, initially we had Ne and N naught, because N naught is the number of phosphorus atoms added per meter cube. Each phosphorus atom will provide one conduction electron. So number of phosphorus atom added per meter cube is equal to number of conduction electron provided by the phosphorus. So here I can say this is 10 to the power 6 into Ne is 10 to the power 16. So it's going to be 10 to the power 22 is equal to, again I can say that is, or I can do like this easily. I can say N naught is equal to 10 to the power 6 Ne for simple approximation minus Ne. So we know that this is 10 to the power 6 Ne minus Ne approximately. So I'll do an approximation, that is equal to 10 to the power 6 Ne. Or if you substitute, this will be 10 to the power 22 minus 10 to the power 16 is almost 10 to the power 22. It's very small compared to 10 to the power 22. So the number of phosphorus atoms added per meter cube is equal to 10 to the power 6 Ne, that is 10 to the power 6 into Ne, that is Ne is 10 to the power 16, 10 to the power 22 per meter cube. So we found number of phosphorus atoms added per meter cube. Now we need to find how many silicon atoms are in 1 meter cube in an intrinsic semiconductor. So we know density equal mass over volume. Density is given. Molar mass is given. So we can find what could be the volume of 1 mole of semiconductor. Okay, so we can find for intrinsic semiconductor, so we know density equal mass over volume, is it? So mass means it's a molar mass, so volume is going to be molar mass over density. So that means this volume indicates the volume of 1 mole of silicon, intrinsic silicon. So I know the number of atoms in 1 mole of silicon, that is the Avogadro number. So number of atoms in 1 mole is equal to Avogadro number 6.0 to 10 to the power 23. Its volume in 1 mole is Ma over rho. So I can find how much of silicon atoms are in 1 mole, in 1 meter cube. So how can I find it? So we know that number of atoms silicon atom in 1 mole is equal to Avogadro number. So I can say Na Avogadro number. That's given in the question. So number of silicon atoms in 1 mole, I know Avogadro number, which is Na. For this is the volume of 1 mole. So why I say it's volume of 1 mole? Because mass I use is molar mass. So mass of 1 mole is molar mass divided by density is the volume of 1 mole of silicon semiconductor. So I can find number of atoms in 1 meter cube. In 1 meter cube of intrinsic silicon is equal to the number of atoms in 1 mole divided by volume of 1 mole, that is Ma over rho, that will be Na rho over Ma. Substitute 6.02 10 to the power 23. Density is given as 2330, I think. Yeah. 2330 divided by molar mass 0.0281. So that will be equal to, we will find 5 into 10 to the power 28 per meter cube. So number of silicon atoms per meter cube is 5 into 10 to the power 28 meter cube. In a pure silicon, in 1 meter cube, there will be this much of silicons. After doping with phosphorus such a way to get 10 to the power 22 conduction electrons, there must be 10 to the power 22 phosphorus atoms should exist per meter cube. So we can find the number, so silicon number, so I can call this number as NSI. Right, so this is NSI is number of silicon in intrinsic semiconductor is 5 into 10 to the power 28 per meter cube. So now I can find the ratio between number of silicon atoms per meter cube to the number of phosphorus atom per meter cube. So I can say NSI, I'll write it here, NSI over N naught. N naught is the number of phosphorus atoms per meter cube to have 10 to the power 22 conduction electrons. That will be 5 into 10 to the power 28 divided by 10 to the power 22. So it's going to be 5 into 10 to the power 6. That means for every 5 million silicon atoms, if we add one phosphorus atom, that is enough to get a conduction electron 10 to the power 22. Or I can say, if we add for every for every 5 million silicon atoms, if we add one phosphorus atom, we can increase the conduction electron of the intrinsic semiconductor by 1 million in the conduction band. So that's the answer we should give. Okay, so here we are going to derive and get few equations. Right, according to the transport equation what we learned in A-level electricity, the current flow through this material, it could be conductor or semiconductor, whatever it is given by I equal NAVE or NAEV, either way we can write EV. So this is the current flow, this is the charge carrier density, that is total charge carriers per unit volume. E is the charge of the charge of the charge carrier. If it is electron, that's the charge of the electron. If it is hole, that's the charge of the hole. This is the drift velocity. Current per unit volume is defined as current density. Current per unit volume is defined as current density. And it is denoted by J. So the unit of J is ampere per meter squared. So J is equal to NEV. That's the current density. Unit of J is ampere per meter squared. Okay, so when there is current flow, there should be external electric field, or there should be electric field inside the material. That means we need to apply a power supply. We should connect the material to a power supply. When there is power supply, it will create electric field inside. So there should be electric field inside that causes the current flow. So the drift velocity per unit electric field is defined as mobility of the charge carrier. So we can say drift velocity per unit electric field, which is stated by the applied voltage across the material. When we connect a battery across it or power supply across it, there will be electric field that drifts the electrons or the charge carriers. So drift velocity per unit electric field is defined as mobility of the charge carrier. So mu, that's denoted by mu, is equal to V over E. That means I can say the drift velocity V equal mu E. So the unit of mu that will be equal to, is the first equation I can say, mu equal, I'll write it later. So the unit of mu is equal to unit of drift velocity, that is, which is meter per second, divided by unit of electric field strength, that is volt per meter. So it's going to be meter squared per volt per second. So that's the unit of mobility. So we came across so far one new equation, that is drift velocity equal to mobility times electric field strength created by external power supply. Current density is equal to current per unit area. So we came across two new equations compared to what you learned in A-level. Okay, so I can write this equation, that current density equation, J is equal to NE. Instead of V, I can write mu E. NE, J is equal to NEV. Instead of V, I can write mu E, where charge carrier density, charge of the carrier, charge carrier. This is the mobility of the mobility of the charge carrier, and this is the electric field created inside the material due to external power supply. Okay, that's another new definition, that is current density per unit electric field strength is defined as conductivity of the material, that is current density per unit electric field is defined as conductivity of the material. So J is the current density divided by electric field strength. To get current density divided by electric field strength gives the current density per unit field strength is equal to Ne mu. This is conductivity denoted by sigma. So sigma is equal to Ne mu. So I can write J is equal to, now instead of Ne mu I can replace by sigma. So the equation will become J equal, instead of Ne mu I can write sigma E. This is actually Ohm's law. In terms of Ohm's law, we learn V equal IR in A level or even IGCSE. But J equals sigma E, also called Ohm's law in terms of electric field strength and the current density. This is Ohm's law. So J equal sigma E is also a new equation. I'll give you the unit of sigma in few minutes after getting a relationship between sigma, which is conductivity, and resistivity. What you learned in A level, R equal rho L over A, where rho is called resistivity of the material. So I'll get a relationship between sigma, conductivity, and the resistivity. You know the unit of resistivity, ohm meter. You had it in A level, all syllabuses had. So after that derivation, after getting the relationship between sigma and rho is the resistivity, sigma is the conductivity, I'll define the unit of sigma. Okay, we know that R equal rho L over A and V equal IR. We know that voltage applied across 2 points is equal to current flow through it, and R is the resistance of the material between those 2 points, where the voltage across the 2 points is V. Okay, and also we know that the electric field strength, when we apply external voltage across the material across 2 points, there will be electric field strength. That electric field strength developed due to the external voltage applied across it is given by E equal V over D, or potential gradient dV over dx. But here we'll use E equal V over D, that is V over, the voltage across these 2 points is V, so E equal V over L. So V, the potential difference, is equal to EL. Okay, so now use these two equations. We can get V equal I times, instead of R I can say rho L over A. V equal this V, I, that I, instead of R I substituted rho L over A. Now instead of this V, substitute EL. So EL equal, instead of V, substitute E into L, is equal to I over A rho L. L and L will get cancelled. I over A is current density. So E is going to be, L and L will get cancelled. I over A is current density, which is J rho. So J, make it subject, 1 over rho E. Now compare this equation with this equation. But already we know that J is equal to sigma E. Where J is the current density, J is the current density, E is the electric field strength created by the potential applied across the material. Same meaning. So here sigma is the conductivity, this is resistivity rho. So we know the relationship now between conductivity and the resistivity that states that conductivity is equal to 1 over resistivity, or resistivity is equal to 1 over conductivity. That is the next equation. Sigma is equal to 1 over rho. So now we know that we learned in A level classes the unit of rho is ohm meter. Ohm meter is the unit of resistivity. So the unit of conductivity per ohm per meter, sorry, per ohm per meter. That's the unit of conductivity. Okay, so I already explained that in an intrinsic semiconductor, uh, the number of holes per unit area is same as the number of conduction electrons in the conduction band per unit area. I told that how the conduction electrons are created at 0 Kelvin. There won't be any conduction electrons in the conduction band in intrinsic semiconductors. At room temperature, electrons will be excited from valence band to conduction band. Whenever an electron is excited from valence band to conduction band, there will be a hole created, a void is created in the valence band. Therefore, charge carrier density of a intrinsic conductor means, actually charge carrier density of an intrinsic conductor means that is due to both electrons as well as the holes. Okay, so there I can see the number of electrons per unit volume, or concentration of electrons or density of electrons per unit volume is same as number of holes per unit volume. That I can say number of carrier density of the that I can say both are A, let it be Ni for the intrinsic semiconductor. Okay, for an intrinsic semiconductor, when voltage is applied across it, the total current flow in the intrinsic semiconductor is sum or the addition of the current due to current flow in the conduction band plus the current flow in the valence band due to hole. So I already explained that. Again, I'll shortly explain that. So if it's the semiconductor, it consists of holes in the valence band and conduction electrons in the conduction band. So if you connect it to a power supply like this, electric field will be developed inside the material in this direction, because this is positive, this is negative. So the electric field will be developed inside the material in this direction. I'll put it outside the material. So we know that electrons will move or will be drift opposite to the direction of electric field. So the electrons will move towards left. So the electrons will have motion towards left. So the current flow due to electrons will be opposite according to conventional sign. The direction of the current flow is opposite to the direction of flow of negative charges. So the current flow due to electrons will be this direction. Okay, I told that already. The hole behaves like a positive charge because it has the intention of attracting the electrons, so it behaves like a positive charges. So the electrons will try to fill the vacancies. So when the electrons are filling the vacancy will move in opposite direction to the flow of electrons in valence band. So there will be current flow due to holes in the valence band. So that current flow will be along the direction of motion of holes, because holes are treated as positive charges. So the direction of holes will be towards right. So the current flow due to holes will be towards right. Now you can see the direction of current flow due to conduction electron and the current flow due to holes in the valence band, both are to the right. So I can say the total current flow in an intrinsic semiconductor I is equal to IE plus IH. So the current density, if I divide the whole equation by cross-sectional area, so I'll get the current density. So the current density J is equal to Je plus Jh. So that means we know J equal to sigma E is equal to sigma E. That's the conductivity of the material due to flow of electrons into the same electric field strength E plus sigma H, the conductivity due to holes motion into E. So all the E will get cancelled. Sigma equals sigma E plus sigma H. But we know that sigma is equal to N, that's the carrier density, into charge of the carrier into mobility. When you think about carrier density, I already told that carrier density in an intrinsic semiconductor, the carrier density of conduction electrons and the carrier density due to holes are the same. So I can say sigma E I can write Ne, I'll replace E by Ni later. Ne, the charge of the electron into mobility of the electron plus NH E mu H. Okay, so Ne and NH are the same. E are the same. Mu and mu H are the same? No, they are different. Actually, mobility of electron and mobility of holes are different. The reason we can say the effective mass of holes is greater than effective mass of electrons, and holes is due to the the motion of holes will be disturbed due to phonons, so the vibration of the atoms. So normally the mobility of holes is lower than mobility of electrons. So mu E and mu H will have different numerical values, different quantities. So Ne I can replace by Ni E mu E plus Ni again, because Ni and Ne, NH will be the same, which is equal to Ni, I put it. So into E, I stands for intrinsic, mu H. So this I can take outside Ne, if I take it, it will become sigma is equal to Ni E into mu E plus mu H. So this is the conductivity of intrinsic semiconductor. I can say sigma intrinsic semiconductor. This is the conductivity. So sigma I for intrinsic semiconductor will be equal to Nie into mu E plus mu H. So resistivity of intrinsic semiconductor, what will it be? 1 over sigma I. So I can say resistivity of intrinsic semiconductor will be 1 over sigma I. So it's going to be 1 over Nie mu E plus mu H. That is for intrinsic semiconductor. Okay. Now, if it is eccentric semiconductor, will there be any change in these equations? Yes, there will be change in this equation. If it is an eccentric semiconductor, what happens? If it is a p-type eccentric semiconductor, I told that current flow is mainly due to flow of holes if it is a p-type eccentric semiconductor, because I told that when you dope a semiconductor, intrinsic semiconductor, to a p-type eccentric semiconductor, there will be larger number of holes than electrons in the conduction band. So there, if it is a p-type eccentric semiconductor, the equation will be slightly different. The current flow due to electrons or current flow due to conduction electrons will be negligible compared to current flow due to holes. So therefore, I can say for eccentric semiconductor, if it is a p-type semiconductor, I can say Jp, p-type semiconductor, Jp is equal to Jh. So if it is an eccentric semiconductor, Jp equal to Jh. So also here I can write J is equal to, for eccentric semiconductor, Ji equal to Je plus Jh. For intrinsic semiconductor, for eccentric semiconductor, if it is a p-type semiconductor, that is equal to Jh. If it is a n-type semiconductor, Jn is equal to, due to only the electron, flow of electron, because if it is an n-type eccentric semiconductor, there will be much larger charge carrier densities in conduction band, and the number of holes per unit volume is negligible. Already explained in the previous when I explained this earlier also. Same way I can say the conductivity of extrinsic semiconductor, if it is sigma p for p-type semiconductor, sigma p for p-type semiconductor, sigma p will be equal to nh e mu h. Same way for extended semiconductor, if it is n-type semiconductor, Ne E mu E, because the other one, the minority carriers, will be negligible. Okay, so these are the new equations compared to what you learned in A level. None of the A levels have these topics, even with Edexcel or Cambridge or International Baccalaureate or even Sri Lankan A level. They don't have these equations. Even Sri Lankan A level, they have electronics, but these equations are not introduced yet. Only they have mainly questions related to circuits. But before starting circuits, I thought it's better to know these basic principles or basic information regarding electronics, because it's a science, so we should know what is happening in semiconductors, why we choose semiconductors when we make electronic components. So I can't avoid it when I teach. If it is not suitable for Sri Lankan A-level students, you can omit up to this part. This part you can omit it. Okay, so now we'll do few questions, around 4 or 5 questions related to this equation, to get familiar with these equations. The numbers are continuous. I already discussed one question related to doping an intrinsic semiconductor with a phosphorus to get 1 million times of 1 million times greater charge carrier density. I already discussed. That is the first question. This is the second question. Okay, so I already derived all these things, so I'm not going to derive it again. But depending on the exam type and depending on the class, whether you are in the university first year or whether you are in A level or anywhere, whatever it is, it might be expected to derive the equations before using them. So you can't memorize all these equations, but I'm not going to derive again, because since I just now only derived it, so nothing actually. You can see that the question, the intrinsic germanium has a resistivity of 0.5 ohm meter. Intrinsic semiconductor resistivity is given, and also the temperature we don't need it. The electron mobility and the hole mobility mu E and mu H are given. We need to find the intrinsic concentration. Ni we need to find it. E is the charge that of the mobility charge of the charge carrier. Here the electron and hole will have the same numerical value of E. So I can use directly this one. Actually, depending on the exam type, you need to derive, but I just now derived it, so I'm not going to derive it again. You can watch it if you want, push the time little ahead and find it. So I'll just directly substitute it. Rho I is equal to 1 over Nie into mu E plus mu H. So rho I, that is the resistivity, is given 0.5, is equal to 1 over Ni. I'll make the Ni subject. Max, no problems. I can write Ni subject or whatever it is, it's not an issue. So 1.6 10 to the power minus 19. Mu E and mu H are given. Mu E is given as 0.39, mu H 0.19. Okay, so we know everything. Find the Ni, that's the carrier density of the intrinsic semiconductor. You will get answer 2.16 10 to the power 19 per meter cube. Okay, so this question also, there are two parts, but first part is same as the earlier question. So I don't need to spend much time on it because already I discussed one question and I have already derived these equations. So find the intrinsic carrier concentration. So here the conductivity is given. So conductivity sigma I is given. So answer I can say sigma I is equal to, I'm using this equation, I derived it already, so I'm not deriving now, I just use it, NIE times mu E plus mu H. So sigma I is given as conductivity 4.3, 10 to the power minus 4 equal to Ni, so that is the question, we need to find it, 1.6, 10 to the power minus 19 is the charge of the charge carrier. Mu E, mobility of electrons, given 0.135, and the mobility of holes 0.048. Okay, solve it and find Ni. You will get the answer 1.47. 10 to the power 16 per meter cube. Okay, the same question, question number 3, the second part, there is current flow through the semiconductor. How much is the current? Not mentioned, but we know the current flow is the sum, SUM, the addition, the sum of the current due to flow of conduction electrons and due to the flow of holes. So here they are saying if the current flow through the through this semiconductor, if a current flows through this semiconductor, then what fraction of this current is carried by the electrons? Okay, so here what fraction of current is carried by the electrons? So we know that current flow or the current density of the intrinsic semiconductor Ji is equal to Je plus Jh, and we need to find the fraction of current carried by the electron. So we need to find Je over Ji, that is equal to Je over Ji means Je plus Jh. Ji equal Je plus Jh. Right. But we know that J is equal to sigma E. We know that. So it's going to be sigma E over sigma E plus sigma H E. E and E in the numerator and denominator will get cancelled. So it's going to be sigma E over sigma E plus sigma H. Also we know that sigma E or sigma is given by generally N E mu. So sigma E, the conductivity due to electron is equal to carrier density due to electron, charge of the electron times mobility of the electron. But we know that the carrier concentration of electron and the hole are the same, which is I denote Ni. So here I can say Je over Ji. Instead of sigma E, I can write Ni, because I can write Ne, but Ne equal Ni, because intrinsic semiconductor will have same concentration of hole and electron, which is I generally denote by Ni. Ni over, so Ni E mu E over Ni E mu E plus Ni E mu H. Because I would have put here Ne E mu E, Ne E mu E, Nh E mu E, but we know that Ne equal to Nh, that is equal to Ni in intrinsic semiconductor. So here all these quantities Ni will get cancelled, so it will become mu E over mu E plus mu H. Right, we are getting the equation, final answer now. So mu E, we know that the mobility of electrons is given by 0.135 over 0.135 plus 0.048. So the fraction, the final answer will be 0.74. That's the answer. So in percentage, I can say 0.74 percentage of the current flow in the intrinsic semiconductor is carried by the conduction electrons. Okay, so this question is related to extrinsic semiconductor. So here the calculated conductivity at 300 Kelvin for silicon with 10 to the power 24 per meter cube aluminium atom. So when you dope it with aluminium atoms, it's going to be p-type semiconductor. So this is regarding to sigma p they are asking. This is p-type semiconductor, its mobility they are asking. Then silicon with 10 to the power 24 per meter cube phosphorus atom. So big part about sigma n-type semiconductor, its conductivity. So just nothing, I already explained and I already derived it. So the equation sigma p equal NH, concentration of holes into charge of hole into mobility of holes. So A part answer for A part, sigma p is equal to NH E mu H. NH is, we know, only thing you need to identify when it is doped with aluminium, will it become p-type or n-type? When it is doped with phosphorus, will it become p-type or n-type? You need to identify, that's all. So after that, just use this equation, sigma p is equal to n concentration of holes into charge of a hole and mobility of hole. So NH is given 10 to the power 24, but they are not telling NH equal 10 to the power 24. They are saying how many aluminium atoms are doped per meter cube. We know that, already explained in extrinsic semiconductors, one dopant will give one electron or one hole depending on the type of doping. So that will give only one, so 10 to the power 24. Each will give one hole. E 1.6 10 to the power minus 19 into mu H, that is 0.048 for holes. Solve it, you will get the answer, that will be 7680 per meter per ohm, or per ohm per meter. That's the conductivity. Then B part, for n-type semiconductor, that is going to be n electron E mu electron. That is same as here 10 to the power 24 phosphorus atoms are doped. One phosphorus atom will provide one conduction electron. So that is 10 to the power 24 per meter cube. Charge 1.6 10 to the power minus 19. And the mobility of electron 0.135. So when you solve, you will get 21,600 per ohm per meter. So you should know how to handle intrinsic semiconductor and extrinsic semiconductor. The condition I already told that. Okay, so this is also related to extrinsic semiconductor. So here they are saying intrinsic silicon is doped with 10 to the power 24 per meter cube aluminium, means it's going to be a p-type semiconductor with number of holes per unit volume 10 to the power 24. The whole concentration will be 10 to the power 24. So this p-type semiconductor is used to make a 1000 ohm resistor which is 12 micrometer thick and 5 micrometer wide. Mobility of holes in silicon given, it is 0.048. Potential of 2 volt is applied across this resistor. Calculate the length of the resistor. So that's the first part. This question has 4 different parts. So we'll discuss part by part. So answer for the first part, we know R equal rho L over A. And we know rho is equal to 1 over sigma. We already derived it here. Sigma equal 1 over rho, or rho equal 1 over sigma. So here the given quantities n is given. So we'll write this one as R equal rho L over A. From this I can say the question is find the length. So L is the question. So L is equal to R A over rho. But we know that rho equal 1 over sigma. So this I can write R A sigma. But which sigma should I consider? I should consider sigma P because majority carriers of this P type is holes. So I can say L is equal to R A sigma P. We know the resistance which is 1000 ohms. Area of cross section means it's like a width into thickness, 2 into 10 to the power minus 6, 5 into 10 to the power minus 6. Sigma is equal to, we know that sigma P is equal to NP or N holes into charge of the hole into mobility of the hole. So we need to substitute that instead of sigma P. So I'll do like this. So I'll write it again here. So that is L equal R K instead of sigma P NH number of holes or hole concentration E times mobility of holes. Okay, if I substitute, I'll get the answer. R is 1000. A, the area of cross section is 2 into 10 to the power minus 6 into 5 into 10 to the power minus 6. That is NH is 10 to the power 24, the whole concentration 10 to the power 24. Is it right? Then E is charge 1.6 10 to the power minus 19 for hole. Charge is 1.6 10 minus 19. Mu H, mobility of holes 0.048. That's all. Solve it, you'll get the length. You'll get the length in meters, that is 7.68 10 to the power minus 5 meter. If you put it in micrometer, 76.8 micrometer. Okay, second part of the question number 5. Find the electric field strength inside the resistor. We know that E equal V over D or V over L. So nothing, we know the potential is 2 volt divided by length. We found it just now, which is 7.68 10 to the power minus 5. So solve it, you'll get 2.64, sorry 60 10 to the power 4 volt per meter. Third part, find the drift velocity of the holes. We got the equation first one, drift velocity equal to mobility times electric field strength. We know the mobility of the holes given electric field strength, we just calculated. So mobility of the holes into electric field strength gives the drift velocity of the hole. So VH is equal to mu H times E. Mu H is given 0.048. And the electric field strength just now we calculated, which is 2.60 10 to the power 4. So that will be 1250 meter per second. Okay, so the last part of this question, find the current carried by the majority carriers. So current carried by the majority carriers here holds. So we know the transport equation I equal NAED. So IH majority carriers is a p-type semiconductor. So IH is equal to NH AEVH. So 8H is 10 to the power 24 because it doped with 10 to the power 24 per meter cube aluminium atoms. So it will be 10 to the power 24 is the whole concentration. Area of cross section 2 into 10 to the power minus 6, width into thickness 5 into 10 to the power minus 6. Charge of the electron 1.6, charge of the hole also same as charge of electron 1.6, 10 to the power minus 19, and the velocity of the holes just now we found it 1250. So the current will be 2 into 10 to the power minus 3 amperes or 2 milliampere. Okay, so that's the end of lesson 1, the first lesson. During the second lesson, I will discuss about formation of PN junction, then forward bias, reverse bias of PN junction, what will happen during forward bias and reverse bias, and what do you mean by forward bias, reverse bias, about PN junction. Then I discuss about diodes, different type of diodes, and their applications, and there will be questions related to rectification, like a rectification type of questions also will be done in the next lesson. After that I'll do about transistors, bipolar junction transistors, field effect transistors. In bipolar junction transistors I'll discuss about amplifiers, then operational amplifiers, and so on until the end of digital electronics. I will continue these lessons. So there will be different lessons that will be in the following lessons. Yeah. Okay, I hope you understood all these things. Thank you. Bye.